Okay, so in the last video we saw the idea behind the Euclidean algorithm, the real Euclidean algorithm, not the sort of short little computational sort of version that we use to do things like compute GCDs in practice. We're going to see an example of that. We saw a few examples of this one first, but now we're going to see an example of how to use the sort of real one to find the GCD of 17 and 3, and we know this is 1, right? This is not a mystery, but to illustrate the process, we're going to see it. Then we're going to see how quickly we could do it the other way, using the first one we saw, and then we're going to think about why we would care about this one, given that the other one is so much quicker and more efficient. Why do we care about this one? And it's so we can find the modular inverse of 3 mod 17. So since the GCD of 3 and 17 is equal to 1, it actually is true that there will be a number that you can multiply 3 by, and it will give you 1 mod 17. And there'll be a number you can multiply 17 by, and it'll give you 1 mod 3. But how do we find these numbers? That is what the extended Euclidean algorithm, which we're going to see in action over here, is for. So first of all, how do we do this Euclidean algorithm thing? Well, we think 17, let's do the division. 17 divided by 3 with remainder is, I think it's going to be 3, that's a horrible 3, 3 times 5 plus 2. All right, it's going to be 3, this is 17, the quotient is going to be 5, well, the quotient is going to be 5, and then the remainder is going to be 2. And so we know that the GCD of 17 and 3 is the same as the GCD of 17 and 2. Or sorry, of 3 and 2, here we go, 3 and 2. And so this is, so then we write 3 is equal to 2 times 1 plus 1. And actually, as I'm doing this, the other one isn't actually going to be a lot quicker. It can be much quicker for larger numbers. I just kind of picked these because it was actually going to be relatively straightforward. Actually, I should make this. I should keep the colors consistent with this. So just pretend this was more computationally annoying. If you try to do it this way with larger numbers, you'll see what I mean. And now we're at the point where we say GCD, we're seeing that the GCD of 3 and 2, which was the same as the GCD of 3 and 17, is the same as the GCD of 2 and 1. So I write 2 is equal to 1 times, and that's 2, right? 1 is a factor of 2, so this is the end process at which we have arrived. This is the 1, that's the 2. So this is saying that 1 is a divisor of 2, so it's the GCD of 1 and 2, which means that 1, the number here, is the GCD of 17 and 3. And again, I know that wasn't actually, this is not much quicker to do it this way. The way that we saw was we had 17 and 3, and we would replace 17 with 17 minus 15, the largest multiple of 3 that we can find, which is less than 17, which is actually also kind of very closely related to the first step here. And this would be the same as the GCD of 2 and 3, which we can then just see as 1. If we want to do this again, we could subtract 2 from 3. This will be 2 and 1, and the GCD of this is obviously 1. So that's how it corresponds. That's why I keep calling this a version of that. It's not. This one on the right is the Euclidean algorithm, but this is, like I'm saying, it's basically the same thing over here. So so this one wasn't a gigantic amount more. Or less computationally efficient. Again, I invite you to try it with larger numbers. But regardless, what is the, or I guess you can just stay there, that's fine. What is the purpose of this? Well, we just found out that the GCD of 17 and 3 is equal to 1. So suppose now, this means that 17 inverse mod 3 exists. That is a thing. That is a thing that is out there that we can find. A number which, when we multiply it by 17 and reduce it mod 3, so look at the remainder it leaves when we divide by 3, we get a remainder of 1. Same thing, 3 inverse, call it 3 inverse mod 17 exists. And strictly speaking, we should call this the inverse of the class, the congruence class of 17 mod 3, and the congruence class of 3 mod 17, these exist. So how can we find them, right? Knowing that they exist and finding them are a bit different. And this one, the real Euclidean algorithm is going to help us find them. How is that? Well, we start at the last line of this thing, which is that, or the second last line, which is that 3 is equal to 2 times 1 plus 1. And our strategy is we're going to use these lines. And this is why I picked relatively small numbers, because it's easier to see when it's and harder for me to make mistakes and confuse people. If we pick smaller numbers, we're going to write 1 as a linear combination of 3 and 17 as some integer multiple of 3 plus some integer multiple of 17, and that's going to give us the modular inverses, and we'll see why. So first of all, so here we have 3 is equal to 2 times 1 plus 1, but what is 2? 2, as we can see here, and that arrow didn't go all the way up, 2 is equal to, so we use the next line, right after using this one, we go up to the previous one, we take 2, it's equal to 17 minus 3 times 5. And then we're going to substitute this in there, and we get 3 is equal to 17 minus 3 times 5 times 1 plus 1. Whoa, the screen moved here on me a little bit. There we go, 17 minus 3 times 5. And then plus 1, and this is 3, and then so we can distribute this out. We get 3 is equal to 17 minus, I'll write this as 5 times 3, because we want to emphasize the multiples of 3 here. This is 3, this is 17, and then let's isolate the 1. We'll subtract off 17, and we'll add 5 times 3. We get 3 times 6, after we add the 5 times 3 to both sides to cancel that off. Then minus 17 is equal to 1. So what do we have here? We have 3 times some number 6 minus 1 times 17 is equal to 1. But what is this telling us? This is telling us that 3 times 6 is congruent to 1 mod 17, right? So we can rearrange this. We can say 3 times 6 minus 1 is equal to 17. So 6 is, or the class of 6 is the class of 3 inverse mod 17. See, what the longer, more computationally involved, I want to say is a nice word, version of the Euclidean algorithm did for us, it allowed us to find the inverse of 3 mod 17. And indeed, 3 times 6 is 18, which is negative 1 mod 17. Which is equal to 1 mod 17, because it's 17 and plus 1. What about why am I thinking about negative 1? Well, how can we find the class of 17 inverse mod 3? Well, we rearrange it the other way. We get negative 17, which is negative 1 times 17, is congruent to, or let's say minus 1, is equal to 3 times negative 6. If we rearrange it like this, then we can recognize that. As 17. There we go. 17 times negative 1 being congruent to 1 mod 3, right? 17 times negative 1 minus 1 is a multiple of 3. That is exactly what it means to be congruent to 1 mod 3, is that you subtract 1 and you get a multiple of 3. These leave the same remainder. And since we're working mod 3, we can actually replace negative 1, because negative 1 is congruent to 2 mod 3. We can say 17 times 2. 17 times 2 is congruent to 1 mod 3. And indeed, this is true. Right? 17 times 2 is 34, which is 33 plus 1, which is 3 times 11 plus 1. So, and this is 1 mod 17, right? That leaves a remainder of 1. So this is a really powerful thing. The extended Euclidean algorithm. We'll do a couple more examples to really sort of hammer this home, to really reinforce this, because the key to one of the things that I learned as a student is that just understanding something once and saying, okay, that's great, and moving on is not enough. You need to go and practice it and think about it and stare at it and work it into your brain until it really sticks. But this is the first step, understanding why this works and the process behind it. And then we can adjust if we get more complicated questions, if we get harder questions where it's not just a straight up application, you have to do something with it. and then memorizing steps isn't close to sufficient. And also you make fewer mistakes, even in the applications, the straight up applications, if you actually understand it. But the idea is that now we know we can, if we understand the Euclidean algorithm, and we understand the extended Euclidean algorithm, how to sort of reverse engineer, although again, I really, really emphasize the practice. Seeing it done and actually doing it are very different things. I found out that the hard way when I was a student. Now we can compute modular inverses, which is a key to solving a lot of number theory problems, a lot of number theory and algebra and modular arithmetic problems. We need to be able to do this. So we will do that in the next video. We'll do a couple more practices of this thing. And then there are going to be a lot of problems coming up where we have to do this, or we're knowing that the GCD is equal to 1 and being able to check it like this using the Euclidean algorithm or the sort of abbreviated Euclidean algorithm is the key to being able to solve the problems. In fact, in a lot of the proofs, we're going to be having using Fermat's little theorem, Euler's theorem, Wilson's theorem, stuff like that over and over again. The fact that relatively prime integers have modular inverses is key to all of those. It's a really central thing in number theory. So this is a really, really important thing to really try to sort of like reinforce and internalize and practice until you know it inside out, upside down, and backwards. And so we're going to be doing some practice in the next video.